Hello, ladies and gentlemen. This is an introduction to the second fundamental theorem of calculus. This will not be a proof of the theorem, but instead we will go through a few examples that should support the conclusion of the theorem. The second fundamental theorem of calculus states that if a function is defined by a definite integral, then the derivative of that function is equal to the integrand, which is a fancy way of saying the inside of the integral. This theorem also assumes that f of t is continuous over some interval from a to b. The example that I would like to use, or the specific problem, will look like this. Let's define a of x to be equal to the integral from 0 to x of 3t squared plus 8t dt. According to the second fundamental theorem of calculus, the derivative of a should just be equal to the integrand, which in this case is 3x squared plus 8x. What I would like to do is to confirm this by using the first fundamental theorem of calculus. If you recall, the first fundamental theorem of calculus looks something like this. If you have a definite integral from a to b of some function, we'll call it little f of t, is equal to big F of b minus big F of a, where f prime of x is equal to f of x, or to put it another way, the antiderivative of little f is big F. The conclusion of the second fundamental theorem of calculus is that a prime of x is equal to f of x. So in order to demonstrate that, what I would like to do is define a of x using the first fundamental theorem of calculus. Once we have used the first fundamental theorem of calculus to define a of x, then we can pretty quickly figure out what a prime of x is. According to the first fundamental theorem of calculus, if a of x is equal to a definite integral, then it can be defined explicitly by big F of x minus big F of 0, where big F is the antiderivative of the integrand, 3x squared plus 8x. In order to continue down this path, we will need to define big F, the antiderivative, which is a pretty straightforward antiderivative, x to the third plus 4x squared plus some constant c. If we plug in x and plug in 0, we will get the result we are looking for. Let's make sure that we're including the proper notation for a definite integral. Big F of x minus big F of 0 can also be written like this. It means the same thing as big F of x from 0 to x. These two expressions are identical. In our specific example, we are evaluating x to the third plus 4x squared plus c from 0 to x. Our final result for a of x will be Let's do this color. A of x is going to be equal to big F of x, which is x to the third plus 4x squared plus c, minus big F of 0, which is 0 to the third minus 4, 0 to the squared plus c. When the c's cancel out, we will just be left with a of x equal to x to the third plus 4x squared. And finally, we can define a prime of x. By the power rule, a prime of x is equal to 3x squared plus 8x, which should look familiar. This was the integrand of the original a of x. One thing that this example demonstrates is that if you define a of x and you'd like to know a prime of x, you don't actually have to find the formula for a of x. The derivative, a prime of x, is simply the integrand. It's the inside of the integral. In this example, we went through the number of steps. We used the first fundamental theorem of calculus to define a of x, just so we could find a prime of x, but it was all kind of unnecessary. We could have just looked at the integral and found a prime of x right away. Now, you might be asking yourself, hey, Mr. Mayhew, why did you choose these numbers? Isn't it awfully convenient that the zeros all canceled out and we were just left with big F of x? That seems a little sketchy to me, and that's a valid concern. So let's quickly go through another example that instead of choosing 0, let's do something from 2 to x, for example. So let's get this out of here, and let's change this. Instead of defining a of x from 0 to x, let's do this from 2 to x, just to see what happens. Do we, in fact, get the same result? Is that number going to change anything? Now, instead of defining this as big F of x minus big F of 0, we're going to do big F of x minus big F of 2. Once again, we are evaluating x to the third power plus 4x squared from 2 to x. X to the third power plus 4x is the antiderivative of the integrand. I did not include the plus c because, as we saw in the last example, the c's will cancel out no matter what we plug in. This time we plug in x, we get x to the third power plus 4x. If we plug in a 2, we get 2 to the third power plus 4 times 2. I believe I made a mistake here. Yes, this antiderivative should be squared, 4x squared. So will we get the same result? A of x is equal to x to the third plus 4x squared minus what? What's 8 plus 16 minus 24? So there's a of x, and sure enough, if we define a prime of x, it's not going to change a thing. A prime of x is still going to be 3x squared plus 8x. The derivative of the negative 24 just turns into 0. The derivative of a constant term doesn't contribute anything, becomes 0. So this does hold. It doesn't really matter what the interval is. The derivative of the integral will always be equal to the integrand. That is the second fundamental theorem of calculus. That's all for now. Over and out.